Hello.
Hello there. Welcome back
Hello.
on a wonderful spring-like last day of January.
How?
There are two handouts today. One of them is the solutions to problem set number 2, and the other is problem set number 3. And problem set number 3 will be due. These are chapter 4 problem. Will be due on Thursday, February 9th. So it gives you a week and a half to make sure. Sorry? What did I do wrong? That's what I said, Thursday. Oh, sorry, yes, no, not 2 days. You get a week and a half. Get a week plus 2 days. Sorry about that. Make sure that we can cover in class all of the material that you need for the homework assignments. The other thing which you should keep in mind is that we are headed up toward the midterm, and we are still on schedule for midterm on Tuesday, February 14th, Valentine's Day. More details about that as we get closer.
Hello, Professor Shustek?
Yes, question?
Yeah, actually I'm getting a little feedback here. But I have a question about the handouts. You said that you just handed out homework number 3?
Yes.
But I had that already, so I suppose I'm missing the handout that I was supposed to have gotten instead of homework number 3 last time. Does that make any sense?
No, it doesn't.
Okay.
What you should have now is handouts numbers 1 through 14.
Okay. What was handout number 12?
Handout number 12 were the lecture notes.
Okay, that's what I didn't receive. Last time I received the homework number 3, which I suppose the rest of the class didn't get.
That's right.
Okay.
Okay. There's an interesting pipeline between us through SITN to the students out there. It seems to be a non-uniform pipeline. We may be able to model that later on in class. If you're missing the handout, call either my administrator, Lily Wan, or call SITN and make sure you get it. In any case, the duplicates of the handouts are all outside my office.
Okay.
If you've got any problems, give me a call.
All right, thanks a lot.
Sure.
Bye.
If you'd much rather be outside today riding your bike, then don't feel bad, because I would too. But we will continue on pipelining. Actually, one of the most wonderful events that happened to me when I was an undergraduate once was on a day like this after a very cold winter, where my physics professor at the beginning of a 2-hour lecture decided that it was much too nice to stay inside a classroom. So he piled us all onto the subway. You can guess which city this was. And we went to the botanical garden and had the rest of our 2-hour physics lecture in the middle of the botanical garden. Which, let's go, he says, right? The problem, one of the problems, is that the television cameras won't follow us. So that won't work. But if you get a chance to enjoy the day today, do so. Okay, last time we had started on pipelining, and we first talked briefly about what a DLX implementation is like without pipelining. Then we went through a bunch of pipelining theory to describe in general how it is that pipelining works and what the techniques are for reliable clocking, and what the speed-ups are that we can expect in best case and in real cases from pipelining. What I'd like to go over just briefly to refresh your memory is what that original DLX implementation looked like, because right now, as soon as we do that, we're going to start looking at how one has to modify it to make it pipelined. So this was the basic RISC machine data path without pipelining that we saw last time. And basically you can see sort of general stages that you have to fetch an instruction through the instruction memory, decode it, feed some of the information to the register files to be able to fetch the registers that are going to be used in that instruction. And remember, because of this wonderful fixed field format of the instruction set, we can decode registers just by feeding those bits from the instruction into the register file without having to be concerned about whether, in fact, those registers are going to be used or not. So, in fact, this is a property that will turn out to be very useful. We don't have to, at this point, when we're feeding the register numbers into the register file, know what this instruction is going to be doing. And the same is true for other operations like sign extension. We can begin the sign extension even if, in fact, these bits that we're sign extending turn out not to be an immediate field at all. They may be register designators or opcodes for an ALU operation. It doesn't matter because in that case we won't use the results of the operation. So read out an instruction, read out the registers, operate with an ALU on some operands, which may be registers and may be other things like the current program counter. A stage where we might be reading or writing to or from the data memory. And then finally a stage where we update things like the registers and the program counter. That's the general flow. We looked also in detail at what happens in that structure at various times. And I realized that there was something that was missing on this chart, which is that down here for a branch, I said that the PC is updated based on condition, and I never showed anywhere where that condition comes from. Well, you remember that for the RISC-like instruction set we're talking about, conditional branches are simply based on whether a register is 0 or not 0. So someplace up after the registers have been read, we need to evaluate whether the register we're testing is 0 or not 0. So we need to add something here like condition is equal to a 0 or a 1 depending on whether the A register is equal or not equal to 0, and whether these are equal or not equal depending on whether it's a branch equal or a branch not equal. And then sometime later, this might be the appropriate spot or it might not be, we can update the PC based on that condition. This notation, by the way, is C notation, and some people think it's obscure, but this basically says that the updated value of the PC is either the ALU or this NPC value, next PC value, depending on whether condition is true or false. It's the general C conditional expression syntax. Boolean, question mark, then value, else value. Yeah?
Is the condition set in that instruction, the branch instruction? I thought the condition was set in the previous instruction.
No, the conditional set in this instruction. Remember, this is not a pipelined implementation yet. This is a single instruction. The branch instruction reads out register A, tests to see whether it's 0, and at the end of that instruction it either updates the PC with the new value or it doesn't. Right. No complications yet. We'll have plenty as we go along. Any other questions? Well, one of the things we looked at just before the end of last lecture was how it is in turning this into a pipeline machine that we would want to break these into stages. And one obvious thing to do would be to break it into stages as shown in this table, which is to say all of this stuff gets done in one stage, this stuff gets done in a second stage, third stage, a fourth stage, and a fifth stage. And we discussed why it is that might not be the best division, and one of the primary reasons was that the length of time that it takes to do all those various stages is not approximately the same. That this first stage, where you're doing both a memory operation to fetch the instruction and register operations to fetch the value of registers, is probably going to be a lot longer than the rest of these stages. And since in a pipeline every stage has to be the same size, we'd be wasting a lot of time in these other stages by making this one big enough to do all of those operations. So in fact, we decided to divide DLX into a slightly different set of stages using these rules. And one of them, as I just pointed out, is that the time of each stage should be about the same as the time of all other stages, because the cycle time is going to have to be the longest of what those are. We have to make sure that each stage is used at most once in each instruction, because there's an instruction in progress in every stage of the pipeline. So no single instruction can do the same thing twice. You can't circle back onto the same stage. You've got to be able to define convenient points to save all the information from one state to the other. And you want to have not too many and not too few. Not too many that the latch overhead dominates. Remember that propagation time plus the skew time and so forth, which is the clock overhead, ought to be small compared to the amount of work that gets done in a stage. And there shouldn't be so few stages that we don't get the advantage of doing the pipelining. So for DLX, what we choose to do is to divide it into 5 stages. And these are sort of the classical 5 stages for a RISC-like pipeline. The first one is instruction fetch, that just pulls the instruction out of memory. Memories tend to be slow, so that's about all you want to do in one stage. Then the second stage, which is the second half of the first box in that table, does what we'll call ID for instruction decode. But there really are 2 functions in there that are going on in parallel. One is decoding the instruction to figure out really what it's going to do, and the other is register fetch, fetching the registers from the register memory, which takes a while. And remember, these can go in parallel because we don't really care what the instruction does at the time that we feed the register numbers into the register file to fetch them out. So having fetched both registers, and now we know what the instruction does, we can proceed to the execute stage, which does anything that requires an ALU. It's an traditional 3-register ALU operation. It's one of the branch operations, anything that requires execution. The fourth stage is only for load and store instructions, and that either loads or stores memory operand into the main memory. The address of the memory operation, of the memory location to read or write, will come from the ALU, and we'll see how that works. And then the final stage is write back. For those operations which modify a register, we at this point write back the result of having loaded it from memory or having computed something in the ALU back into the register file. Yeah. Yes, you're right. It is slowing them down, and in fact, for, let's say, an ALU operation that doesn't need the memory cycle, it would be nice not to do it. The problem is that all of the instructions, and we'll see that in a second, are proceeding in lockstep down the pipeline. If you remove the memory stage from one of the instructions, it's going to collide with the next instruction, which is already in write-back. You can't sort of get ahead of each other. Let's see how that works in graphical form, and I think you'll understand why that kind of thing is difficult to do. Now, in fact, I'm going to go through an argument that says you can't do it, and I'll show you why, and you'll believe me. But then in about a week, we'll go through different kinds of more advanced pipeline organizations that, in fact, allow you to do exactly that to get higher performance. Well, this is a way of describing what's happening in a pipeline instruction, which we'll see a lot of. So you need to become familiar with this kind of diagram. And basically, this is a diagram that in 2 dimensions shows how the pipeline is filled and executes from one stage to another. Time is moving in this direction. So these represent cycle 1, cycle 2, cycle 3, and cycle 4. And in this direction, instructions are being added to the pipeline. So the first thing that happens in cycle 1 is that the first instruction, instruction I, enters the top of the pipeline and starts its instruction fetch. In cycle 2, that instruction moves on from instruction fetch to instruction decode, and the next instruction starts executing in instruction fetch. In the next cycle, the instruction 1 that was in decode moves into execution. Instruction I+1 that was in instruction fetch moves into decode, and a new instruction moves into instruction fetch, and so on. At any given time, the instructions which are in the pipeline are those that are represented by a single vertical column. Remember, time is moving this way. So the first point at which the pipeline is full is when we get here. So finally, at this point, we've got the pipeline fully occupied. The first instruction that we entered with the pipeline at the beginning is I+4, and it's way down, I'm sorry, the first instruction that we entered was I, and it's way down in the pipeline, up in the drawing, at the write-back stage, indicating it's ready to write back its registers. The one before that is the one after that is in the memory stage, the one after that is in the execute stage, and the latest one, the one we just added to the pipeline, is in the instruction fetch stage. We ought to actually draw this the way, let's draw this in another way, because this will turn out to be useful later. instruction fetch, instruction decode, execute, memory, and write back. And in fact, this is our pipe. And we can draw it as a pipe that looks like that. And in fact, it's one-dimensional. It's a little bit deceiving to look at that previous drawing and see, in fact, that it's a two-dimensional object. Remember that the pipe itself is simply one-dimensional. I think I actually brought some instructions with me. Right. Okay, here are some instructions. And remember that all that's happening is that instruction 0 starts out coming down the top of the pipeline. When instruction 0 moves into decode, then instruction 1 moves into instruction fetch. When these two move down, then the next instruction moves into instruction fetch, and so forth. Remember that nothing is happening in 2 dimensions. It's only a single-dimensional pipe plus time. Now, this may look like a sort of trivial exercise right now, but as we begin to elaborate what happens in the real pipeline, you'll see that things get a little more complicated, and sometimes it's actually handy to draw a piece of paper and put pennies on it to actually follow the flow of instructions. But this, in fact, shows us what happens. Let's back up the pipe a little bit. There we go. Nice thing about this is that you can move forward and backward in time. This shows us what would happen if we tried to do what you suggested, which is, let's say that instruction 0, well, let's move the pipe one down again. Let's say that instruction 1 is one that doesn't need to do the memory cycle, and as this was moving down, you'd like to skip that cycle and move it from execute into write back immediately. Well, it can't do that, because instruction 0, which let's say was one that needed to do mem, is doing the write back, and you can't have 2 instructions in the same pipe stage at the same time. So our simple model of a pipe is that every instruction has to go through every stage, regardless of whether or not it really needs that stage, because otherwise it's going to collide with instructions before it or instructions after it. Any questions about that? Okay. I think I'll hold on to my instructions in this pipeline because we'll use it later. Okay, so how do we implement that pipeline execution with the data flow model of the DLX machine that we had before? Well, this is our first attempt. We take the same picture we had before, and we lay on top of it the boundaries between the different stages. So that if one instruction is currently executing in this instruction fetch stage, and its instruction is currently being fetched out of memory, then the instruction that was issued before that one, the older instruction, is currently in the instruction decode stage. The one before that is in the execute stage, the one before that is in the memory stage, and the one before that is in the write back stage. So this is instruction I, this is instruction I plus 1, this is instruction I plus 2, this is instruction I plus 3, this is instruction I plus 4 at any given time. Now, one of the things that means is that everything you need to know about instruction I plus 2 had better be stored in this latch register in between the ID and the EX stage, because all of the other stages have information about different instructions. So this has to be a completely self-contained unit that knows everything it needs to know about instruction I plus 2. And everything that you need to know about I plus 2 in the future as it moves into subsequent stages. And in fact, if I were to just put registers on all of the lines that cross my vertical bars, that would not do it. It would not work. For example, down at the write back stage, I have to make a decision about whether I write back to the register memory the output of the data memory, because it was a load instruction, or the output of the ALU, because it was an ALU instruction. Well, I don't have anything stored in my pipeline register here that tells me that. All I have is the output of the memory and the output of the ALU. What I need is information about what the original instruction was. Well, I've got this instruction register back here in the IF stage. Why don't I just look at that? Well, the answer is it's the wrong instruction. That's instruction I plus 4. It's not instruction I. So in fact, what you've got to do is to carry along with this pipeline, and in each of these latched stages, every bit of information, including the original instruction, or pieces of it, that you need to be able to execute later stages of the pipeline. Okay, here's a question. There are 5 pipeline stages, and at the end of each pipeline stage you have to advance to the next stage. Why do I only show 4 sets of latches in between stages? Where's the 5th one? Anybody?
You don't really care because the instruction's done for that time.
You mean for this time? You mean the write-back time? Yeah, that's the one that's missing, and in fact, the latch for that stage is in architectural registers, so-called. It's in the machine, the part of the machine that you really care about, which is to say the registers, the program counter. I'll leave it at that. The registers, which get written at the end of the write-back stage primarily, and perhaps the program counter, which in a simplified model could be written as well at the end of the write-back stage, which is sort of the way I showed it here, if this is meant to say that there's a latch over there that holds the output of this branch multiplexer.
Question?
Yeah.
I don't see how even in the simplified model you can write a program counter 5 ticks after the instruction, because then you'll have loaded the same instruction 5 times without advancing the program counter.
Yes, that's one bug. The other bug, there are several bugs in this thing. This is why I said on the top that it has bugs. That's one bug, in fact, that the program counter got updated in the normal case too late. The other bug is that in the case where you're doing a branch, the program counter got loaded too late too, because you've already executed 3 or 4 instructions beyond the branch by the time you reload the program counter with the target location. So, it's all right, we'll fix those problems. Don't build this machine as it stands, right yet. Before we show how to fix this design and make it work as a well-pipelined machine, I also want to point out that you can use this kind of design, and it is often used, for non-pipelined machines as well. You could, rather than implement the machine in a single cycle implementation that we did originally, you can in fact use this kind of structure to build a multi-cycle non-pipelined machine. Now, why would you want to do that? Well, sometimes you have to. Remember that our simple model of the DLX processor was that you fetch an instruction, everything propagates through combinational logic, and then at the end of it you clock the results in, the output of the registers and so forth. Well, in some instruction set architectures you can't do that. You need to update results as you're executing in intermediate stages, like the auto-increment or auto-decrement instructions of the VAX. So that as you're executing the instruction, you have to update partial results before you can continue executing the instruction. So that's one reason why you might want to use that structure in a multi-cycle implementation. Another is that you might want to reuse some hardware units for more than one part of the instruction execution. Remember, we showed a separate ALU to add operations for an ALU instruction, and then another object, an adder, to compute PC plus 4 to produce the next PC. And we had to do that because we were clocking all of those results at the end of one big cycle. Well, if you have multiple cycles, then in fact you might be able to reuse hardware units if they're used in more than one part of an instruction. So you could use the ALU to increment the PC plus 4, as well as using it later on to do the ALU operation, as long as you have multiple phases separately clocked. The other thing, and this was a point, in fact, that was raised by somebody in class last time, was that often external units, especially big memories and I/O devices, are themselves clocked units, and you have to wait and synchronize with them, and having an internal multi-cycle phase for the instruction makes that much easier to do. The other is to simplify timing analysis. Rather than to try to treat the whole thing as one big gestalt and compute worst-case paths through the entire execution of the instruction, you can divide it into smaller segments, which are easier to analyze. And in fact, most reasonably complex processors, even if they're not non-pipelined, wind up using some form of this kind of multi-cycle clocked instruction execution, rather than a giant single cycle, as I showed earlier. But notice that there's a penalty that you pay for getting these advantages, and that penalty is that in general it's going to be slower. And it's going to be slower for 2 reasons. One is that each segment in that cycle, or each cycle in the execution, has the clock overhead, the latching overhead that we talked about. And the other is these quantization effects, that because you can't divide it at places such that each stage is exactly the same size, you wind up wasting some time in some of the cycles because you had to make cycles big enough for everything. Now, in fact, if it's not pipelined, you could design a machine where the cycle time for each part of the instruction varied depending on how much actual work there is to do in that particular cycle. But that gets to be a very complicated machine to design and to debug. So after that aside about non-pipelined machines, let's go back to making our pipelined machine. And look again at the rules for what these pipeline registers are and what the constraints are. Well, one thing, as I mentioned, is that each stage must be independent. So these interstage registers have to hold everything you need to know about the instruction. That includes data values, values of registers and data to be going to memories and so forth. Control signals, which might include instruction fields that have been decoded. Certainly will include things like controls on the muxes to say which inputs to the mux should be picked. Controls on the ALU to say what operation the ALU is currently is to be doing, an add, a subtract, a shift, and so forth. And in fact, for many of these things, you have a choice to make about how you want to propagate these control signals. Many of them are functions of fields in the original instruction. So in fact, because a control might be some function of instruction fields, I1, I2, I3, and so forth, you can either pre-compute a control value, a single bit, let's say, that controls whether a multiplexer should flip one way or the other, back in instruction decode. And then along the pipe, you can propagate that decision rather than computing it again later. Or you can propagate the entire instruction and through the pipe. And any stage that needs to compute some control information, a mux control or an ALU control, can recompute it based on the original bits in the instruction. And in fact, you can make that decision based on which stage you happen to have free time in to be able to do the computation, and whether or not that stage has all of the appropriate information to be able to compute the result. Now, I said that one of the things in dividing the execution into stages was that you had to make sure that everything is used in only one stage, that the ALU is only used at one stage in the instruction and so forth. Well, in fact, we have a problem with the register file, because the register file is used in two places. It's used in the instruction decode stage to fetch operands, and it's used simultaneously, but for a different instruction, in the write-back stage to write back the updated register. And in fact, the way to think about this is that the register file is in fact two independent units, and that you can simultaneously do a read of two operands and a write of one operand at each clock cycle. So that our requirement to make this pipeline work is that the register file has two read ports and one write port, and that they can all operate simultaneously. And this I mentioned, that there is no final set of registers after write-back because its results are stored in the architectural registers of the machine. Okay, with those rules in mind, let's elaborate the pipeline diagram to show specifically what it is that gets latched between each stage of the execution and follow the data flow. I've simplified some things in this diagram compared to the previous diagram in order to be able to leave it uncluttered, but I think all of the relevant pipeline stages are here. In the instruction fetch, you fetch the instruction from memory. It gets latched in the pipeline registers at the end of instruction fetch. And my notation for this has been simply to number them based on which pipeline stage. So the latches between the instruction fetch and the instruction decode are two latches. Are number two latches. So we have instruction register 2 and PC2, which memorize the value of the instruction and the value of the incremented program counter at the end of instruction fetch. The textbook uses a little more cumbersome notation that each of these registers is denoted by the two stages that they sit between. So this would be a latch that would be IF/ID dot something to indicate which latch it is. But we're talking about the same thing. Notice that as we move from stage to stage, some of the information simply gets propagated from place to place. So I said, for example, that we need to keep the instruction bits itself moving down the pipeline from stage to stage, because anytime we have to compute something based on it, we have to use that instruction and not the one that's several stages earlier being fetched out of instruction memory. So in order to create a pipeline, which, by the way, is one of the things you're going to be doing in programming assignment number 2 that you'll get next week, you have to create these chains of latches, and in each stage of the pipe you move information from one latch to the equivalent latch in the next stage. So this is the chain of instruction registers, and this is the chain of program counters that move down from place to place. In addition to the instruction itself, you may in fact at any of these stages be computing some control information. And if I were to do that here, for example, I would compute some control information based on perhaps the instruction register and anything else that's going on for this instruction in this stage. And then I could start a chain of control information and have it move down the pipeline from stage to stage if I needed that information later. This is a kind of example of that. I decided, because I had the free time available in instruction decode, to do the sign extension of an immediate field. Whether or not, in fact, it happens to be an instruction that has an immediate field, I do that anyway. So I peel off some of the bits in the instruction register, I sign extend them, and then I begin storing that in inter-stage latches in order to be able to pass it down the pipeline. In fact, in this case, it gets used directly in the next stage. So I compute in the ID stage the sign extended immediate field, I latch it at the end of instruction decode into this register, and then when this instruction has moved into execute, I can consume that information by feeding it to the ALU if it's the appropriate instruction. And I don't have to pass that information further down to pipeline stages because there's no need for it. I either used it or not used it in the execute stage and I'm done. Yeah?
Why does there's two different types of immediate fields, the longer ones for the jumps.
Yes.
So how does the sign extension know whether to fill the whole thing from bit 16 up or just from 26
One of
up?
the reasons, the places where I've suppressed detail here, this sign extension thing, in fact, has to look at some other bits in the instruction to see what kind it is, and based on that, know how to do the sign extension. Notice that the register inputs here are actually two. There are two sets of 4-bit fields going to read out two separate registers marked A and B. Notice, for example, that the write-back address, this is an important point to notice, that although the register file is being shown in the ID stage, the writing of the result register is actually happening in the write-back stage in time. So in fact, the address of the register to be written can't be derived from the instruction which is currently in the ID field. It has to be derived from the instruction that's currently in the write-back field. That's what this line is for. The register number which is to be written has to come from the instruction in the write-back field and go back into the register file in order to write the correct register number. Now notice, in fact, that I've suppressed a bit of detail here that I showed on the previous diagram, which is that there is a multiplexer here that chooses one of several different sources for that register number. It can appear in two different places in the instruction based on the instruction type, and it also could be constant 31 for jump and link instructions. But all of that information is, even if we just save the instruction register, all of that information is contained within the instruction which is currently executing in write-back. Any questions or comments? Yeah.
I have a question about the program counter, the way it marches down there. For one thing,
we haven't fixed that yet, but go ahead.
Okay, well, it gets incremented before, and then it gets used.
Yes.
So wouldn't you need the original program counter to do your jump from rather than an incremented one, or is that somehow worked into the...
You're talking about the jump and link instruction?
No, I mean the branch. It comes down, the PC3 comes down and goes as input into the adder.
PC3 comes down and goes input into the adder, right?
So wouldn't you want to have an unincremented program counter at that point?
Yes, you do want to have an incremented program counter, because remember, for conditional jumps or for branches in general, the immediate field is added to PC plus 4 in order to compute the target.
Okay.
So what's coming down the pipe is in fact PC plus 4. That part works okay. There are other things that are broken about jumps and branches here.
Well, it seems strange that it goes out after PC3. It goes to PC4, but it never gets used out there.
Oh, you mean this PC4 never gets used?
Well, you answered my other question, but
Right.
yeah, that's another question.
Okay. Yes, in fact, that's a very good point, that this PC4, I don't show it being used anywhere, or for that matter, PC5. But in fact, PC4, you should understand, needs to be used. And it's what I mentioned just before. It's the jump and link instruction. Right? When you do a jump and link, you've got to take PC plus 4 and cycle it back into the register set somehow. So in fact, PC plus 4 for this instruction, I guess in fact it could be PC plus 5, needs to get written back into the register file. And in fact there is, I guess you don't need PC plus 5, there is in fact a multiplex path here which is not shown, which is that the data to be written back into the register file can either be the output of the memory, or it can be the output of the ALU, or it can be PC plus 4. So in fact, there's a path there, which is not shown for purposes of simplicity. And that shows why PC4 is needed. PC5 is actually needed only in more bizarre cases of interrupts, where you have to save the currently executing instruction to be able to resume it later. That's a good question. Any others? Okay. The next table shows some of the details of what computations get done at each stage and what things get latched in each of the registers. And I don't want to go over this in great gory detail. There's an equivalent chart like this in the book. In general, the rule here is that any register which you want to write in stage n is based on some function of inputs of the register at stage n minus 1. And sometimes, if it's a chain, like the PC chain or the IR chain, that function is a no-op. It just passes it on from one level to the other. For example, here in the execute stage for load and store instructions, we're just passing on the value of the PC in the previous stage to the PC in the next stage. In other cases, we're actually doing some computation. So here, for example, the register labeled ALU4 is computed and latched at the end of this stage to be A3, which is the previous latch for the A output of the register file, plus IM3, which is the previous latch for the extended immediate field of the instruction. So in general, all these boxes do is to compute some function of the registers on their input and put the result at the end of the cycle into the registers on their output. And if you ever see a reference in here for something which is further back than n-1 or further forward, then you have to look at it with a wary eye, because there's something funny going on there. Any questions about this? I don't particularly want to go over the details. This bit of notation for immediate is meant to show sign extension. So the immediate 3 is meant to be the 15 low-order bits of the instruction register, which is IR2 because it's the end of the decode stage, plus the 15th bit, counting from the right, repeated 16 times. So this represents sign extension of a 15-bit immediate field. Okay, so that's what happens at each stage in the pipeline, and as people have pointed out, it doesn't work. This pipeline is still broken.
A question?
Yeah.
Going back to, about the pipelining.
Yeah.
What if you have a branch going down that has a condition to jump to some other memory location, but you're still executing instructions?
Yeah.
When we get to the end, the last stage, and you decide you're going to jump,
Yep.
You've been executing you have another 4 instructions coming down the pipeline.
That's right. And in fact, you probably should not have executed those 4 instructions because they're after the jump.
So what if you
I'm sorry?
Well, as they come down, you might be writing to memory that you're not supposed to be writing to.
That's right.
So.
That's right. That's why it doesn't work. And that's why the title of the next slide says, unfortunately, this pipeline is broken. And in fact, we'll see how to fix that. But that's exactly one of the major problems with that. Branches and jumps don't work. The PC gets updated about 4 cycles too late. And tell me you didn't read the next slide before you asked that question. You didn't. Okay. All right. That's exactly one of the major problems. And in fact, in general, branches and jumps are the single biggest headache for designing pipeline machines because they don't work right. You want them to work right away. And we're going to show a compromise technique that allows you to do the branches a lot earlier than the write-back stage, but you still can't get it to happen as soon as you'd really like it to happen. So in fact, we're going to wind up modifying the instruction set in order to cater to the pipeline's implementation so that we can get it to go fast. And we'll see how that works later. That's one problem. Another problem that nobody's mentioned so far is that an instruction which uses the result of the instruction before it, let's say, won't get the right data. Because one instruction may be writing a register, for example, and that's going to happen in the write-back stage. The next instruction, let's say, wants to read those registers as part of the input for its operation. Well, it already read its registers 2 or 3 cycles ago when it was back in the ID phase. So in fact, it's not getting the registers that got updated by the preceding instruction. It's getting registers that are old and stale with the wrong data. So that's another serious problem that we have to fix before we can build this machine and sell it to our customers. There's a general solution to these kinds of problems, and that solution is that you've got to be able to stall the pipeline. You've got to be able to stop all or part of the pipeline for a while until you can, for example, get the data that an instruction needs as a result of the previous instruction, or so that you can figure out where the branch or jump is going to go, or if it's going to go. So you've got to be able to stall all or parts of the pipeline. And there are 2 different general reasons why you might want to do that. One is that there are unexpected sort of external delays. We've been assuming that if you want an instruction, you fetch it from memory and it comes back in 1 cycle, or if you want data, you fetch it from the main memory and it comes back in 1 cycle. Well, in fact, that only works when those are fast caches and we get a cache hit. If we were to get a cache miss, then in fact, it's going to take several cycles to get that data back, and you've got to stall the pipeline to wait for that to happen. The other kind of problem that causes stalls is what we were talking about here, which is that some part of the pipeline has to wait for something that's happening in another part of the pipeline. And there are 3 basic kinds of things. One are the data hazards. That's these, where it's waiting for the right data. The second are control instructions, where it's waiting for the right instruction to occur. And we may not be able to proceed with executing other instructions until we figure out what the branch is doing. And the third is, which is something that doesn't happen in the example pipeline that I've shown, is that there may be a hardware resource which is currently in use for another instruction that you have to wait for it to finish with before you can proceed. Now, we were careful in designing our pipeline in order to make that not happen. But as we add more complicated instructions, in particular as we add things like floating point, it's not going to be possible to do that. And occasionally there are going to be pieces of hardware that 2 different instructions executing the pipeline might want to access simultaneously, and we're going to have to stall part or all of the pipeline in order to be able to wait for that to clear up.
Question?
Yeah.
Would that be true with the memory, or wouldn't memory have to be multi-ported? Same thing like the register file, because during the memory stage, it's also doing instruction fetch.
Yes. If there was, in fact, one memory for both instructions and data, we've got exactly that problem. We've got a structural hazard for the memory. And in fact, that's why most modern microprocessors are designed with its separate instruction and data caches. So you can simultaneously be doing an instruction fetch out of the instruction cache and a data read or write out of the data cache, and those don't represent a structural hazard. There were some earlier machines, like the original Spark implementations, that didn't do that. In fact, they had to stall the pipeline any time an instruction was reading or writing memory, and that wasn't such a wonderful thing to do. Very good point. The alternative to that is, in fact, to build a memory which is a single memory that has multiple read and write ports, the way our register file does. It turns out for big multi-level cache memories, that turns out to be an expensive thing to do. It's difficult to do that. Now let's go back to our pipeline drawings and see what it looks like to freeze the pipe for these various stages. This is the same kind of drawing we showed before. Let's say that when we get to cycle 5, this happens to be the first cycle where the pipeline is completely full and we've got 5 different instructions executing in 5 different stages. Let's say that what happens here is that this reference to memory for instruction I+1 causes a cache miss. And it can't complete in one cycle because it's got to wait for the cache miss to be processed and for the real data from main memory to come out. Well, one of the things we can do is just freeze the entire pipeline, which means that everything that's going on in cycle 5 also goes on in cycle 6. The instruction fetch that happened in 5 either gets redone or actually nothing happens into the next stage. And so for instruction decode and execute and memory and write back. In fact, we wouldn't have to do this for write back. Since write back is not waiting for anything, we could allow write back to continue in cycle 5 and do nothing in cycle 6. It really doesn't make any difference. The basic idea is that cycle 5 and cycle 6 are essentially identical. So all stages of the pipe are frozen in lockstep for one or more cycles. If, in fact, you're going to do write back in cycle 6, you should suppress it in cycle 5. There are some operations which, if you do multiple times, will cause problems. This is sometimes called a fixed pipe or a frozen pipe stall because the entire pipe and the relationship of all instructions are frozen and maintained exactly the way they were in the cycle before. This works okay for cache misses. It does not work, however, to remove the other kinds of pipeline hazards. If instruction I+3 is waiting for the data for instruction I+2, it hasn't gotten any advance on it. It hasn't allowed instruction I+2 to continue while instruction I+3 doesn't continue. So it only works well for sort of external events that freezing the whole pipeline will do something useful for. One of the things I guess I could point out is how in a Verilog-like simulator one might freeze this pipeline. Let me do a short diversion into what pipelining and latching might look like in Verilog, and I'm going to simplify this a little bit. But now that you're all Verilog experts, having done the first programming assignment, you'll recognize statements like the following. A simple D edge-triggered flip-flop in Verilog might look like something like this. That whenever there is a positive edge of the clock, you assign the output of the flip-flop to be what the current input of the flip-flop is. At every clock edge, you basically copy, memorize the D inputs to the flip-flop, and with zero delay in this model, produce outputs for the next stage on the Q output. So that's the basic form that a pipeline latch could take in between stages in a pipelined implementation. If you want to do a freeze, then all you need to do is elaborate this to depend on some global signal that says whether or not the pipeline is currently frozen. So you could say something like, if pipe frozen, then set Q equal to D. Basically, you've turned it into a no-op for the case where the pipe is frozen. And this is a simple kind of stall.
Wouldn't you want a not?
If pipe frozen, then yes. If not pipe frozen, then Q equal D. Otherwise, don't change Q. Leave it the way it was before. Now, in fact, this is a very simple edge-triggered flip-flop, and probably to make life simpler for the second programming assignment, it's going to be recommended that you use a slightly more complicated form of latch that basically separates the memorization of the input from the setting of the output. Remember, the deep edge-triggered flip-flop memorizes its input on the rising edge of the clock, and then instantly, or with a short propagation delay later, the output changes. What you'll wind up using to simplify your life, mostly, is a two-stage kind of master-slave flip-flop, where the rising edge of the clock memorizes the input, but the output doesn't change until the falling stage of the clock. But all of that information will be part of the handout for the programming assignment. So that's the way to do a global pipe freeze in a Verilog type simulation. Pretty simple stuff. Now let's look at the next level of complication in stalling, and that is delaying an entire instruction. Let's say that for some reason instruction I+2 can't even be issued. Let's say that it was a case where, as you mentioned before, that instructions and data come out of the same memory, and some previous instruction, I guess in this case it would have to be I-1, is actually fetching from memory, so that I+2 can't do its instruction fetch. Well, in that case, what you can do is simply stall the entire instruction pipeline after that one by basically simulating a no-op. I mean, I've written it here to say that instruction I+2 stalls for one cycle and begins its instruction fetch in cycle 4. Another way of saying it is that there's sort of an instruction in here, which is instruction I+1.5, which is a no-op instruction. And instead of fetching something from memory in cycle 3, you force into the pipeline a no-op. And in fact, it turns out that for RISC or DLX-like processor that we've been talking about, a no-op is just all zeros. So in fact, the way you can implement this is simply to insert into the top of the pipeline, the first stage of the pipeline, a cleared instruction register, and then let the rest of the pipe continue. That no-op then proceeds down the pipe. In cycle 3, the no-op is in the instruction fetch stage, and in cycle 4, the no-op, which we don't see here, is in the decode stage, and 5, it's in the execute stage, and 6, it's in the mem stage, and 7, it's in the write-back stage, and finally it exits the pipe, having done nothing. But the effect is that we've separated instructions I+1 in all previous instructions from instruction I+2 in all subsequent instructions by one extra cycle. So if there was some reason why we needed to do that, because of dependencies between the instructions or because we couldn't fetch instruction I+2, we've accomplished the goal. In a Verilog-like model, you could do that by saying something like, for that particular pipe stage, always at the positive edge of the clock, if this particular stall signal is on, then clock the flip-flop with its input. Else, the output is not the clocked input, but is in fact a no-op, which might be all zeros in the case of an instruction register, if you're inserting a no-op at the beginning of the pipe. So basically, based on a signal, you decide to propagate the input of the register to the next stage, or push a no-op into the pipe. Now, as long as we're doing this in the first stage of the pipe, we don't have to worry about what happened in prior stages, because there are no prior stages. But in fact, the next case we're going to show is one where there are prior stages. And in fact, we want to insert a no-op into the pipe, but we want to insert it into the pipe in the middle of an instruction. Here's a case where I+2, back in cycle 3, got to do its instruction fetch and got to do its instruction decode. But let's say that for some reason, maybe it needs some results from a previous instruction that aren't ready yet, it has to stall. So in fact, we want to insert a no-op into the pipeline in the middle of the execution of instruction I+2. Basically, I+2 and all later instructions, including I+3, have to stay in the state that they're currently in. So I+2 stays in instruction decode in this state. I+3 stays in instruction fetch in this case, in this state. And what we've inserted is a bubble into the pipeline. And that bubble, at this point, is in the execute instruction. So I+2, instead of moving to execute, stays in ID, and this no-op instruction gets manufactured in the middle of its execution in the execute stage. In the meantime, prior instructions, like I+1 and I, proceed. So I+1 moves from execute to mem, I moves from mem to write back. All subsequent instructions are frozen. I think this is a point at which it's time to bring back our pipeline and our instructions to see, in fact, what's going on. In this case, in fact, I've got instruction I in the mem stage. I've got instruction I+1 in execute. I've got instruction I+2 in ID. And I've got instruction I+3 in instruction fetch. And at this point, something's going wrong with instruction I+2, and it needs to wait for something that's going to happen later. Well, instruction I and I+1 move into the next stage. A no-op is inserted in the execution stage. It's essentially a bubble inserted into the pipeline. During that cycle, the previous instructions are basically frozen. So in a Verilog-like model, you would have to say that these guys do nothing. The stages prior to the one that the bubble is being inserted into don't move at all. The one that the bubble is being inserted into becomes a no-op. So its pipeline register, sitting over here, gets zeroed. And the next two stages move normally. So it's essentially as if the top part of the pipe underwent what we saw originally, which is a total pipe freeze. The middle section of the pipe underwent what we saw in the second case, which was a conversion to a no-op, and the rest of the pipe continues to move as it does normally. From here on, we're done. We've inserted the bubble into the pipeline, and we don't have to worry about it anymore. We just, for all subsequent stages, continue to execute as if nothing had happened. So in the next stage, everybody moves down one, a new instruction moves in on the top, and this bubble gradually percolates down the pipeline and then falls out the bottom, having done nothing except separate later instructions from earlier instructions. All understand that? If you have any problem, I'll lend you my pennies. So that's the way we can stall pipeline to get around some of these hazards. Let's look at some of the hazards again individually in more detail and see when it is that stalls can be used to fix them and when it is we can do other things. So remember, we talked first about structural hazards. Structural hazards occur when two instructions at different parts of the pipe somehow have to use the same hardware. And that may happen because you decided not to duplicate the hardware as much as is necessary. There may be, our example register file in our case had exactly one write port. Well, that was fine for our DLX instruction set because registers are only written in one place, and that's at the write back stage. If this were a VAX or something that had for auto increment instructions or other instructions that modified registers at multiple places, that wouldn't work. And we could then choose to treat the register file write port as a structural hazard. And when two instructions in different parts of the pipe both needed to write to the register file, we would have to handle that hazard by stalling, presumably. The other is a resources that is not fully pipelined. It will turn out that you'll see for a lot of the floating point operations, which are complex and require expensive hardware, that you can't design them reasonably to allow a new instruction to start on every cycle. So in fact, if you have two instructions that are close together, both wanting to use division, they may be too close to start another division, and that represents a structural hazard. Well, one fix that always works is to stall. Anytime you've got a later instruction that needs something that an early instruction is already using, just stall the pipe, as we showed. It's the low-cost solution. It increases the average cycles per instruction, so it's best to be used only for things that are relatively rare. Things like floating point division. Things maybe, depending on how rare you think they are, like multiply. Things probably not like fetching data for instructions and for data references. In fact, the Spark V1, as I mentioned before, made that decision and probably was penalized about 20 or 30% for doing it, because something like 30% of instructions wind up making a memory reference. That means that 3 out of every 10 Spark instructions are going to have to stall waiting for this structural hazard to be resolved between instructions and data. So if you don't want to take the penalty, then you have to duplicate the resource. Costs more, but preserves cycles per instruction, keeps it down. It's certain. Question?
On the Spark, why did they decide to do that? What was their reason for doing that?
Because they didn't want separate caches. They had limited chip area, and they didn't want to build 2 separate caches, one for instructions and one for data. That takes a lot of space. Caches are big, you know, they're 4K, 8K, 16K, something like that, and they chose not to use the area for that. Duplicating is best done when the thing you're duplicating is cheap. And an example which we've already seen for that in our case is the fact that we're not using the ALU to get PC+4 in the case that we need it. Rather than using the same piece of hardware, adders in particular, because they're not even general purpose ALUs, are pretty cheap devices to build, so we give the PC its own adder rather than trying to share it. Another example which we've seen in our implementation is a register file with multiple ports. We can read 2 registers and write 1 at the same time. The other fix is to take an expensive resource, which you can't make multiple copies of, and make sure that you can pipeline it. That in fact, even though, that you can start a new operation in that resource on every cycle. And if you've done that, that's essentially the same as duplicating the hardware. And you've removed the structural hazard. And a lot of the floating point units try to do that, although sometimes it's difficult. Now, one of the things that we've seen in the DLX is that, in fact, whether or not there are structural hazards depends strongly on the design of the instruction set. And the VAX was a terrible case for pipelined implementations because it has structural hazards all over the place. The DLX architecture is great because every resource that an instruction needs is used only once, it's always used in the same pipeline stage, and it always takes 1 cycle. And if you do that, if you design your instruction set to have that happen, then in fact you've avoided structural hazards altogether. The VAX is a particularly bad case because it has multiple memory operands, for example, each of which may take several instruction or data references for memory indirects. And in order to avoid structural hazards to memory in a VAX, you would have to have a data memory, for example, that has probably 6 or 8 simultaneous read ports. And that just is not practical to do. Those are structural hazards. What about the other kind of hazards? Data hazards where one instruction depends on the result of a previous instruction or maybe a next instruction. Well, one of the primary rules is that we cannot allow the pipelined implementation to affect what the instructions actually do. From the programmer's or compiler's point of view, it must appear as though instructions are executed separately and you don't start one until the previous one is complete. Well, where do we get into trouble? There are 3 different kinds of data hazards that are named based on what behavior we expect to see or what the instruction semantics require. One is the read after write, and that's sort of the traditional data hazard, which is that an instruction tries to read a register that a previous instruction has written. So if we had an add instruction, for example, and it produces its result into register 0, and a subsequent subtract instruction produces its result anywhere, let's say register 1, but uses register 0, we have a potential of a read after write hazard. Because remember, these instructions are being executed in parallel. I guess we'll see the example of this later. The add instruction has not yet written its result in register 0 by the time the subtract instruction has gotten around to reading what it wants to be the updated register 0. If you don't fix this, then in fact the later instruction, in this case the subtract instruction, gets the wrong value. So we have to fix that. The second kind of data hazard is a write after read hazard. And that happens in a case where an instruction reads a value. Let's say this instruction reads register 1, and the following instruction writes register 1. The problem is you've got to make sure that because these things are executing in parallel, that the second instruction hasn't written its result before the first instruction reads it. If you do that, then the first instruction is sort of the complement of the previous case. The first instruction gets the wrong value. In this case, it's the new value it's getting incorrectly, rather than the old value. And in fact, I'll show later that this is not a problem with our current pipeline, but in fact can be a problem and is a problem often in other pipelines. Another kind of data hazard is the write after write fault. And that's a case where you've got two instructions that are both modifying the same register. Let's say I've got a divide instruction that produces a result in register 0, and sometime later I have an add instruction that produces a result in register 0. Now again, this is not something that can happen in our pipeline, but in some pipelines it could be that the add instruction writes its result to register 0 before the divide instruction writes its result to register 0. The result being that the final value in the register is wrong, and any subsequent instruction that uses register 0 will get the result of the divide instead of the result of the add.
One note about register 0.
Say again?
On the DLX, if you try to write...
Yes, register 0 is a bad example in all of these things. Replace register 0 in all of these examples with register 8, because in DLX, register 0 is always 0. Thank you. Let's look in our pipeline diagram of how a read after write hazard might occur. Here's a sequence of instructions. The first instruction is one that produces its result in register 1. So in fact, it does its operation during execute. That's when its operands are being added. But register 1 is not written back until cycle 5. Well, the following instruction is using register 1 as one of its input operands. And registers are read in this pipeline implementation during instruction decode. So in fact, the results get written back into the register 2 cycles too late. So sub gets the wrong value. The next instruction also happens to use register 1 as one of its operands. Its instruction decode comes a cycle later, but in fact it's still too late. Right back for the add instruction hasn't happened or won't happen until cycle 5. The next instruction also uses register 1. Well, here we're closer, in fact. The write back is going to happen at the end of cycle 5, but depending on where you think the write back occurs in relation to the read of the registers in the register file, this AND instruction may or may not get the right results for register 1. In the sort of traditional pipelined implementation where things happen only on the end of the cycle, it's going to be too late. The register 1 won't be written until the end of this write back cycle, and register 1 needs to have been in the register file during this instruction decode for the AND instruction to get the right results. So in fact, in this example, all 3 of these instructions are broken, and they get the wrong result. Finally, 4 cycles later, we have another instruction that uses register 1. It fetches it in cycle 6 during its instruction decode, and here we're absolutely safe. The values have been written into the register file during cycle 5. They can therefore be read out in cycle 6 by the XOR instruction without any problem. So in fact, we have to do something to fix the problem for 3 of the instructions that follow the add. And we'll see a little bit later how to fix that. Let me just convince you that, in fact, the other two kinds of hazards are things that we don't have to worry about in the DLX pipeline, but in fact may happen in other pipelines. And I guess I showed a sort of example like this. A write after read hazard is one that can happen if in your pipeline it's possible for instruction to write its result early compared to other instructions that read their results later. Let's say that this is a VAX-like instruction set where the divide takes a while, and in fact the result of the divide goes into memory indirect through register 1. So this divide gets going and is going to take a while to execute. In the meantime, add begins its execution. Early in its cycle, it's going to be writing a register because it's auto-incrementing register 1. So sometime back in its instruction fetch, it has modified the contents of register 1. When the divide finally gets around to finishing and fetches register 1 in order to do its store, it's got the wrong value because register 1's already been incremented. So this is an example case where in another instruction set architecture you can have read after write hazards. And in fact, it doesn't even have to be as complex as a VAX-like instruction set. In DLX, this can't happen because all the reads occur always early, they're in the ID stage, and all the writes occur always late, they're in the write-back stage. So it can never happen that a modified register is used and fetched by an earlier instruction. Is that okay? You all believe me? Similarly, a write after write hazard can happen when a fast operation follows a slow one. Let's say that we have a divide instruction that takes a long time and it writes register 0. We may or may not do something later on that tests register 0, but then the add instruction that follows also writes register 0. If the divide instruction is still in progress at the time that the add instruction completes and writes register 0, we have a write after write hazard. Again, this can't happen in DLX, at least in the integer implementation of DLX. We'll see that it can happen in floating point operations because there's only one write back stage, and because instructions always get to that write back stage in the order in which they were originally executed. So in the order in which the programmer or the compiler wrote those instructions, that's the order in which they get to the write back stage. So these registers are always stored in exactly the same order that the instructions were issued. It's nice when that happens, but it doesn't always happen that way. We're about out of time. Next time we will talk about the read after write hazards, which do exist in DLX, and how we can fix them.